Hello everyone. In this video I'm going to be reviewing how to solve a trigonometric equation with a modified argument. In this case, my modified argument for my cosine is theta over 3 minus pi over 4 over the interval from 0 to 2 pi. So for a problem like this, it involves several steps because we have to consider several possibilities because of the modified argument. To start simply though, I'm going to substitute and say I'm going to look at this as if it were cosine of x equals 1/2. This will give me some base values to start from. So I need to think what rating for cosine, what cosine value of a rating gives me 1/2. I need to consider my 30, 60, 90 or my 45, 45 right. And given that it's 1/2, more than likely it's my 30, 60, 90. And I can see that for cosine, I would choose cosine of 60 degrees, or pi over 3. So pi over 3 is my basic radian measure. Now since I want cosine that's positive, cosine is positive in quadrants 1 and 4. So in addition to pi over 3, using my reference angle, I also have 5 pi over 3 as my initial possibility. So again, I start as if I were solving cosine of x without the modified argument, and my two base values are pi over 3 and 5 pi over 3. Next, I'm going to apply the modified argument to each of these values, and I'm also going to add to each one of these plus 2 pi k. 2 pi, of course, being the period, even though normally that expression is reserved for the phrase find all solutions. I'm going to use it to help me specify these solutions that I want. And as I cleared out my work here, so again, here's my pi over 3 and 5 pi over 3 plus 2 pi k. And over here on the left are my modified arguments. This is what I substituted for x in each case. So instead of having x equals pi over 3 plus 2 pi k and so on, it's now the original argument, what I originally wanted to solve for. Now I want to isolate the theta in this case, whatever my variable actually is. So to do that, I'm going to first of all remove my pi over 4 to each side by adding it. I'll need to find a common denominator, which among these two would be 12. So I have to multiply my first fraction by 4, my second by 3, and I'm having 4 pi over 12 plus 3 pi over 12. So now I have 7 pi over 12 plus 2 pi k. Now I still have my theta over 3 equals 7 pi over 12 plus 2 pi k. Let me clear some of this out. To solve this, I have to multiply each side by 3, which includes my 7 pi over 12 and my 2 pi k. So what I'll end up with is theta is equal to 21 pi over 12 plus 6 pi k, and since I can reduce 21 and 12, I'll simplify that fraction. I reduce each of them by 3 and get 7 pi over 4. Here's my first possible set of solutions. My second, I'll do the same thing for my 5 pi over 3. I'll add pi over 4. Similarly, I'll need a common denominator of 12, which will end up giving me 20 pi over 12 plus 3 pi over 12. So now I have theta over 3 equals 23 pi over 12 plus 2 pi k. Again, I'll multiply each side by 3 to solve for theta, and I'll end up with theta is equal to 23 pi over 4 plus 6 pi k. So this part is mainly algebraic. I needed a common denominator. Then I multiply each side by 3 to isolate my theta, just like I would any variable. And again, I'm getting 6 pi because not only do I have to multiply the theta and the 7 pi over 12, or the 23 pi over 12, but I also have to multiply the 2 pi k attached to each one of them. That's where I get 6 pi k. So these represent all possibilities. Now I'm going to use the k values of -1, 0, 1, and 2, like I'll always do for these kinds of problems, to find a few cycles of periods that will give us solutions. And then from those few solutions, I'll pick which ones I want in my overall answer. So again, I always use -1, 0, 1, and 2 for k. So when I say k is -1, this becomes -6 pi, which when I get a common denominator of 4, for each one of these, it's subtracting -24 pi over 4. So when I subtract 7 minus 24, I'll get -17 pi. When k is 0, it's just 0, so nothing changes there. When k is 1, again I'm adding 24 pi over 4. When k is 2, I actually have 12 pi, which is 48 pi over 4 that I'm adding. So for k is 1, when I add 7 and 24, I get 31 pi over 4. For when k is 2, 7 plus 48 gives me 55 pi over 4. So these are my first set of 4 individual solutions, covering a pretty wide range. I do the same thing for 23 pi over 4 plus 6 pi k. When k is -1, this becomes -6 pi, and just like before, this is -24 pi over 4 that I'm adding, which is where I get -1 pi over 4. When k is 0, 23 pi over 4. When k is 1, back to 6 pi, so I'm adding 24 pi, which is where I get 47 pi over 4. And when k is 2, I'm adding 12 pi, which is equivalent to, again, 48 pi over 4, which is how I get 71 pi over 4. Now I want to find these solutions that are in my original domain. The original domain was from 0 to 2 pi. When I look at all my possible solutions, 7 pi over 4 is the only one that falls in that range. So my only solution in this case is 7 pi over 4. So again, with these questions, I want to start off as if it were just a standard basic trig equation, get my potential values, add on my period k, solve for theta in each one. That's all this work is, and end up with theta equals 7 pi over 4 plus 6 pi k, and equal to 23 pi over 4 plus 6 pi k. I chose the values for k, -1 to 2 for each one, and found 4 possibilities for each possible solution, for each possible set of solutions, and from those I picked whichever ones fall in the appropriate domain, which was only 7 pi over 4.